Hi everyone. In this video, I'm going to work on kind of a tricky piecewise problem. I'm going to give you a piecewise function, and I'm first going to try and find an equation for the function itself, and then the tricky part comes in. I'm going to try to find an equation for the area trapped under the function up to a given x coordinate. So let me start with a simple piecewise function. In fact, just a simple function. It's not even piecewise. I'll just restrict the domain. And then we will try one that's a little trickier that actually does have pieces. Okay, so here's my first function. I'm just going to make it a straight line, and it's going to line segment, start at 0, 1, and then it's going to go to let's make it go 1, 2, 3, 4, 5. Okay, so first let's find an equation. I'll call this y equals f of x. Okay, so for this one, I have a linear function, and conveniently my y-intercept is given. So I'm going to go for slope-intercept form. Oops, go ahead and do that. And I can tell from my graph that the value of b is 1. And I should also be able to count out, I didn't label that, but that's 4, 5. So if I go over 4, I also go up 4, which means my slope is also 1. So the equation for the function is just f of x equals x plus 1. But because it's clearly showing that it gets cut off at x equals 0 and x equals 4, I'm going to go ahead and include that as well. This is for 0 less than or equal to x less than or equal to 4. Okay, on to the slightly trickier and I think more interesting part. We would like to be able to write an area function. And this area function tells me how much area I've trapped under my curve if I have covered everything from x equals 0 to any x coordinate in this interval. So let's just say, for example, I decide to cut it off right around here, and my area will look like this. So it's a little trapezoid, or I'm going to try and make that even easier. If you know trapezoid formulas, you can go for that. But I would just look at it as a rectangle with a little triangle sitting on top. If I decide to cut off my area here, what I'm going to get is actually just a bigger trapezoid. So it's the same shape, it's just larger. So we want to make this a function where wherever we decide to cut it off, and I will always cut it off with a vertical line. So if I decide to cut it off at this specific x value, can you tell me how much area I've caught? So I want area as a function of x. Okay, so again, it doesn't matter which trapezoid you're visualizing. Both of them are the same thing, trapezoid or rectangle with a triangle sitting on top. So I'm going to go ahead and use the big one. So when I look at this, first thing is to realize that what's happening is no matter where you cut it off, you always get the rectangle on bottom. So I want the area of the rectangle plus the area of the triangle. However you set this up to begin with is up to you. Just this is what I'm thinking when I go to set it up. If I want the area of a rectangle, I'm looking for a length times a width. And if I want the area of a triangle, I'm looking for 1/2 of a base times a height. Okay, so for the rectangle, one of those dimensions is definitely really easy. In fact, I actually think both are fairly easy here. If we're looking at this, we'll call this one the length. That's already given for me. If I cut this off at x, that means I've got a base on this shape of x units. So the length of my rectangle is x. The width of my rectangle is going to be like a height here. The width of my rectangle looks like it's always going to be 1. So there's my length times width. For the triangle, the base of the triangle will be exactly the same as the base of the rectangle. So this is the base of the triangle. So that is also an x. The height of the triangle is right here, and I can see a couple of ways to get it. One is that this point is on the graph of f of x equals x plus 1. So this point, if the x-coordinate is x, the y-coordinate is x plus 1. So the entire height from here all the way down to the x-axis is an x plus 1. Which means if I only want the height of the triangle, I would take x plus 1, the entire height, and I would subtract off 1, and I'm actually just left with x. That's one way to get it. Another one that I can spot, and there certainly could be more, is that you can take advantage of the fact that you know something about the slope of this line. The slope of this line is 1. And this triangle is actually a perfect little slope triangle. If you fit this triangle right up under the curve, then the base of the triangle is a rise and the height of the triangle is a run. If you have a line with a slope of 1, that means your rise and your run always have to be equal. So that as well would lead me to the conclusion that the height of my triangle is also x. And then we can simplify a little bit. And that's my area function. Okay, so hopefully we're feeling okay about that one. I want to do a little trickier one. I think these are pretty cool, but I know they're challenging. So the trickier one will actually get something piecewise going on. We'll see if we can figure it out. Okay, so let's say my function starts at 3, 0, has a straight line segment that drops down to, I think I said that backwards, starts at 0, 3, has a straight line segment that drops down to 3, 0. It then shoots back up to the point 4, 2, and is then horizontal from 4, 2 all the way to 6, 2. So this is 4, 2. This is 6, 2. Okay, so this is my function. And again, I'm going to do this in 2 parts. First, I want to find the equation. So let's call this y equals g of x. Okay, so first thing that makes this a little trickier is that g of x is definitely piecewise. It's made up of 1, 2, 3 different pieces. So let me give myself my brackets for my piecewise function. I'm just going to go left to right. So my first piece is this one right here. This is a line with a y-intercept at 3 and a slope of -1. You have to go down 3 and over 3 to get to this point. So that's going to be a -x plus 3, or a 3 minus x, however you want to look at that. Okay, hold on. I see that this is being blurry for whatever reason. Let's see if we can get it to look better. A little bit better. Okay. The next piece of this function, also a line segment. This one has a slope of 2. If I go over 1, I have to go up 2. So it's a 2x. And then you choose your method for finding the y-intercept. You could set up y equals 2x plus b and plug in the point 3, 0. You could work your way backwards. Say, okay, I have to go back 1, down 2, back 1, down now a total of 4, back 1, down a total of 6. And you can also just kind of do some trial and error. If you want it to go through 3, 0, then when you plug in 3, you're going to get 6. You'll need to subtract 6 to make that back into 0. So that's the equation for the second line piece. Oh, we should put restrictions. The first one goes from 0 to 3. This equal to sign on the 3, I don't really know if I should include that point on the first line segment or on the second line segment. It doesn't really matter. So just decide that you're going to say this closed circle is on the end of the first line segment or it's on the beginning of the second line segment, and it will be fine. You really shouldn't do both because you shouldn't have to look at 2 pieces of an equation for one input. But here, because they do meet up, even that isn't that big of a trouble. Okay, the second piece, since I included x equals 3 in the first piece, I'm going to exclude it from the second one. And then I need to stop at 4. And again, you get to make the decision about which piece gets to claim 4. I'm going to go ahead and put it with the middle piece. The last piece is actually really easy to find an equation for. It's a horizontal line. What's always true about points on that line is that their y-coordinate is 2. So this is just has equation y equals 2, and that holds for x is bigger than 4 and less than or equal to 6. Because I chose to include the 4 in the middle piece, I won't include it in the last piece. I do need to include the 6 because there's no other piece to take that on, and I want a closed circle. So there's the equation for G. Where things get interesting is when I go to trying to find the area equation. So let's say we want to find an equation for the area A trapped under the curve. So let's just say trapped under G on the interval 0 to x. So again, the idea would be we can choose any x coordinate as our stopping point. Anything between 0 and 6 would make sense here. And wherever we stop, we want our formula to then calculate how much area is underneath the curve, between the curve and the x-axis, and between x equals 0 and x equals 6. So you can imagine it as this is something that we're trying to paint, this area underneath this curve we're trying to paint in. If I stop painting at a specific x coordinate, how much paint have I used? Okay, so I'm going to set this up. We'll see if I have enough room to squeeze in here. Because the function changes shape at a couple of different locations, the area that we're painting is going to change shape at those locations. So we're going to need the exact same number of pieces for the area function here as we did to get the original function. If we stop painting somewhere, and it can be anywhere, between 0 and 3, what we'll be getting is kind of similar to the last one. We have a negative slope, so it's kind of flip-flop the direction the triangle is sitting, but it's a rectangle with a triangle on top. If x is the x coordinate that we stop painting at, then I'm picturing x right here. So if I want to get this area, so let's see here, I'm going to snag in a piece that I can do a little scratch work on over the top of G. If I want to get the area of that triangle on top of a rectangle, I know the base of the triangle is x, and I need the height of the triangle. So here's the deal. The height of the triangle, I can't just pick anything I want. It's determined by where I hit the line. And that line was y equals 3 minus x. So if this is x coordinate x, my y coordinate is going to be 3 minus x, or negative x plus 3, which means the height of the rectangle is 3 minus x. So in this problem, my rectangle doesn't always stay 1 unit high like it did up above. In this problem, if I make my x coordinate close to 3, I'm going to get a really short rectangle. If I make my x coordinate close to 0, I'm going to get a really tall, skinny rectangle. So the height of the rectangle changes as well as the width. For the triangle, we need 1/2 base times height. Base again is x, just like the bottom of the rectangle. And then you have the same choice as before. You could say, all right, well, this entire distance is 3, and the height of the rectangle is 3 minus x. So if you subtract a 3 minus x from 3, see if I'm getting off my page, not yet. If you subtract a 3 minus x from 3, the 3's will drop out and you'll actually just get an x in there. The other option on this one again is to say, okay, I have a slope of -1, which means whatever my run is, my rise will be the opposite. We don't really care about direction. Did we go up or down for this triangle? We just care about how long each side is. So a slope of -1 still means that the two sides of your slope triangle will be exactly the same length. The negative sign that slope takes on is just to show that you have to go down and right instead of going up and right in the last one. So either way, you should get that this is actually also x. So back over here, I have x times 3 minus x plus 1/2 x times x, which is going to simplify a little for me. 3x minus x squared plus 1/2 x squared, which is 3x minus 1/2 x squared. Okay, so the area, if you cut off your painting somewhere between 0 and 3, while you're still just sitting under the triangular part of this wall, is going to be 3x minus 1/2 x squared. And this is for a cutoff between 0 and 3. If we decide to instead cut off our painting somewhere between 3 and 4, what happens is we get the entire first triangle. We don't need any x's involved. It's 3 by 3. We cut that in half to get the area of the first triangle. That's all painted. The x part becomes interesting because we may get more or less of this second little triangular piece. So now, if my x is going all the way out past 3, what I really want to know is how long is the bottom of this triangle. So if it's x units to get to this far outside edge, and it's 3 units to get to the inside corner of that triangle, this distance right here is going to be an x minus 3. So the big distance x minus this little distance 3 leaves us with an x minus 3. Okay, so here I'm going to use my scratch paper again. Here, let me hide the other mess that I had. And I'm going to say, for the big triangle, I know it's 3 by 3, so its area is 1/2 of 3 times 3. For this little triangle that I'm now working on, I've decided that the bottom of the little triangle is an x minus 3. So I'm adding on a 1/2 base x minus 3, and I need a height. So this is all determined by the second line, and the second line was a 2x minus 6, which means if this corner is sitting at an x coordinate of 6, the height of this thing is 2x minus 6. Another way to get at this would be to say I have a slope of 2 on this segment. So if the bottom of the triangle is x minus 3, if the run is x minus 3, the rise has to be 2 times the x minus 3, and that will give you the exact same result. So either way is fine with me. In fact, now that I'm looking at it, I kind of like this 2 times x minus 3. So I'm going to go ahead and trade out. And the reason I like it is because here, when we multiply, we get 9/2. And then when we multiply here with the 2 sitting out in front, we can actually go ahead and cancel that. We have a 1/2 times an x minus 3 times a 2 times an x minus 3. You can rearrange the order of multiplication whenever you want to. So I just get a 9x plus x minus 3 squared. I'm sorry, 9/2 plus x minus 3 squared. So if I stop painting this wall or shape somewhere between 3 and 4, then I will get this much area. If I plugged the x coordinate I stopped at in, this would tell me how much area I've painted to get up to here. Okay, so the final piece is, what if I've painted the whole first triangle and I've also painted the whole second triangle, and I decide to dead end somewhere inside the rectangle? So again, this could be anywhere. I could just get a little tiny piece or a big piece of this rectangle. Important thing to realize is that I can calculate the area of both triangles, and all I'm trying to calculate here is the area of a rectangle. So if I'm looking at big triangle, which is 3 by 3, the little triangle, we've got the whole thing now, so there's no x to worry about here. This is 1, and this is 2, and then we have some part of a rectangle. So we need to know how long the base of this rectangle is. Let's see if I can make that actually end. And what the height of this rectangle is. Okay, so I have 1/2 of 3 times 3, that's my 9/2 again, for the first triangle. I have 1/2 of 1 times 2, that's my second triangle. For the rectangle, the base of this rectangle, okay, so let's see now, x goes all the way from 0 out to here. Let's see if I have another color I can read. I don't have another color. So again, x is the x coordinate we stop at. So this is scenario number 3. We've painted the entire first triangle and second triangle, and we decide to stop somewhere out here in the rectangle. So x goes all the way from here to here. I know that from here to here is 4. So this is x minus 4. So the base of my rectangle is an x minus 4. The height of my rectangle, that part's actually easy. It's a rectangle. This is a horizontal line. It's always too tall. So I'm just going to sneak that 2 in the front. And I can simplify a little bit. I get 9/2. This just cancels out, plus 1, plus, I'm going to go ahead and distribute here because I think this will combine nicely. X minus 8. Okay, so let's see. What do I have? I have 4.5, 5.5. Minus 8, so negative 2.5, which is 5/2. Okay, let me just see if I believe my own self. 9, and then 8, 16, 25, 26. Oh, wait. Minus 9, I think I believe my own self. 9. Minus 7. Maybe I don't believe my own self. 4.5 minus 7. I think I may have lost the 1 in there. Okay, hold on. Clearly Maya needs to do her fraction workout. So I have 9/2, and then I'm adding 2/2, and then I'm subtracting 16/2. Okay, so 9, 10, 11. Minus 16 is negative 5/2. Oh, I was right all along. I should have trusted myself. Okay, so 2x minus 5/2. So this is a simplified formula for how much paint I've used if I paint both triangles and part of the rectangle. And the x coordinate that I stop at determines how much of the rectangle. So this is for any x between 4 and 6. Okay, so hopefully that's enough to get you started. I know those are tricky, so absolutely send me questions as you have them. I think that's it. Thanks for watching.